Hello, we're looking at page 251, numbers 1 through 7. Got the radius and area. Need to relate dAdt to drdt. So we got area equals pi r squared. Take the derivative with respect to t. That would be derivative of the area with respect to t equals pi as a constant. So you have 2 times pi is 2 pi. Then just r to the first. And then, of course, dr dt by chain rule. I'll do just fine. Interesting that that's the formula for circumference. Question number 2. Surface area. Radius r and surface area of a sphere related by the equation s equals 4 pi r squared. Write an equation that relates ds dt to dr dt. So the surface area equals 4 pi r squared. Take the derivative with respect to t. Ds over dt equals 4 pi is still a constant, so 2 times 4 pi is going to be 8 pi. R to the first, and then chain rule with r is dr dt. Volume, radius, height, and volume of right circular cylinder related by the equation v equals pi r squared h. dv dt to dh dt if r is constant. So we take our initial equation that the volume is equal to pi r squared h. We are presuming that r is constant. And we want to relate dh dt to dv dt. So we take the derivative with respect to t on both sides, get dv dt. So h pi is what we're looking at. So 2, so let's rewrite this. This would be like h pi r squared, where all this is the constant. So 2 times pi, or h pi, is 2h pi r to the first dr dt. Our A and B want to relate dv dt and dr dt, presuming h is constant. So we're going to presume that, whoops, I did that wrong. I did A for B and B for H. Alright, so the first one, R is constant. So we're not going to look at this. My fault. Scratch, 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 scratch. Alright, so this is just this derivative. So H. So the derivative of V with respect to T, all this is constant, so that just comes out front. And it's times H, but just like the derivative of 2x is 2, derivative of pi r squared h is just pi r squared. But of course the chain rule makes it so that we have to do dh dt. That's the proper answer to A. In B, now we're looking at V and R with h constant. So that's what we're doing before. So let's take V equals pi r squared h. So h is constant. And change that one into h pi r squared. So we have the constant out front. You don't have to do this, but it just makes it sit outside there a little more obviously, like the coefficient here and there. So 2 times that when we take the derivative, dv dt. So that's 2h pi, or 2 pi h. And then an r to the first, but dr dt. Alright, so it's 2 times h pi, so 2 pi h. And then r to the first, so that drops down 1, dr dt. We have a C? Yes, we do. How is it dv dt related to dr dt and dh dt if neither r nor h is constant? In that case, we have to use the product rule. So we're looking at v equals pi r squared h. And so we'll take pi r squared as the first term and h as the second term. So when we differentiate, so pi r squared, the derivative of pi r squared with respect to t would be 2 pi r dr dt. The derivative of h with respect to t is going to be dH dt. All right, so from here we can do first times the derivative of the second times the derivative of the first. So shall we do. dV dt equals the first times the derivative of the second plus the second times the derivative of the first. Then just clean it up slightly. We got pi r squared dH dt plus 2 pi r h dr dt. All right. Good, good. Number 4, electrical power. Power in watts of an electric current is related to the circuit's resistance in ohms and current in amps by the equation P equals Ri squared. So we're looking to relate dP dt and dR dt, di dt. We already have an equation that has P, R, and I in it. So when we differentiate, we'll get dP dt, we'll get dR dt, and we'll get di dt. So number 4, power equals resistance times current squared. Take the derivative. dP over dt equals the first times the derivative of the second plus the second times the derivative of the first. So quick cleanup. 2 R I di dt plus I squared dr dt. R I R, however you want to do it. So that was A. Has them all related. And in B, we want to relate dr dt and di dt, presuming that the power is constant. So we're talking about if the power is constant, that means if we increase the resistance, we have to decrease the amperage by the power of the square, or by the power of the square root. If we increase the amperage, we have to decrease the resistance. Or an increase in amperage results in a decrease of resistance, or an increase in resistance means you have to increase the current to get the same power. You don't have to know that, but there's a lot in there. All right, so looking at P equals Ri squared, and to relate dr dt to di dt. So we can take the derivative. We're assuming that P is constant, so the derivative of the constant is 0. So we have the first times the derivative of the second, chain rule, plus the second times the derivative of the first. Big R. All right. I'd like to relate those. They are related. It'd be nice to have everything in terms of I's and R's. So how do we wish to do that? Yeah, it's all in R's. It's fair. It'll work as is. We can clean it up a little bit, or we can do it as a negative. We can divide by R, or divide by I, because that is a constant, I suppose. So negative 2R. So we're just subtracting this term here. Negative 2RI di dt equals I squared dr dt. We can get rid of an I on both sides. So that gives you negative 2R di dt equals I dr dt. And that's about as good as we can do right there. We could solve for one or the other, but it's not necessary. Right? Do 4, number 5. Talking about diagonals. X, Y, and Z are lengths of the edges of a rectangular box. Common length of the box's diagonals is S equals the square root of x squared plus y squared plus z squared. How is ds dt, dx dt, and dy dt, and dz dt all related? Well, take this equation. Basically we're talking about from one corner to the other, but S equals the square root of x squared plus y squared plus z squared. Really should recognize this. I mean, if you have a box, rectangle, say, talking about x, y, and z, then this distance here is going to be the square root of x squared plus y squared. Right? That's the distance across the front. But then if you look at a plane that goes through those corners, plane that cuts across here is those. So we're talking about a plane that goes like this. Right? So from corner to corner to corner to corner to corner. Plane that runs through that plane, if we look at it on edge, this is going to be the square root of x squared plus y squared. This is going to be z squared in length. So we're talking about this distance here. So we're talking about from this point, bottom corner, to this point, top corner. So that's up in there. And when you do the Pythagorean theorem on here, we got this length s, and s is equal to exactly this. Because it's this squared plus this squared, square root, sorry, z. This squared plus this squared, square root. Right. So that these two cancel, we get x squared, y squared, z squared. And then take the square root of both. Take the square root of both. So that's what a common diagonal is. Anyway, relating them, let's just take the square root, let's just differentiate both sides with respect to t. But first, we'll take this as x squared plus y squared plus z squared to the 1/2 to make it easier. So ds dt, so the change in the length of this measurement here from bottom left to upper right with respect to those is going to be 1/2 x squared plus y squared plus z squared to the negative 1/2, and times by chain rule 2x dx dt and 2y dy dt. Oops, I have to move this y up to there, I guess. Plus 2z dz dt. Right, so we got this goes on the bottom of a fraction because of the negative. This goes on the bottom fraction because it is. ds dt leaves this on top, so it's going to be 2 dx dt plus 2y dy dt plus 2z dz dt all over this 2, so we can obviously do some canceling here, over the square root of x squared plus y squared plus z squared. And when we cancel it out, we get ds dt equals x dx dt plus y dy dt plus z dz dt all over the square root of x squared plus y squared plus z squared. All right. Seems reasonable to me. Number 6.